Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussions related to this course, Introduction to Electronics. In the last lecture, we had seen basic operational characteristics of a diode. And if we want to use a diode for within a circuit, then we need a model for that particular diode here. So in this particular lecture, we'll look at a simple model for a diode, which we can use to analyze a wide variety of circuits. So in the forward bias, we had said that the diode can be expressed in this particular form of expression here. I equal to Is exponent Vd by Nvt. N is the ideality factor. Vt is the thermal voltage here, Kt by Q. And we can represent this in this particular expression in this voltage dependent current source here. Okay, so I mean the voltage is across the same pair of terminals as the current here, and it's a nonlinear current source. And along with the current source, we had also seen that the diode has capacitance within it. So for the sake of completeness, we have added the capacitor also in parallel to the this current source here. Okay, so now most of the time, at least in this particular course, we'll be looking at circuits which have either DC voltages and currents, or even if they have AC voltages and currents, the frequency is so low that the impedance of the capacitor 1 by omega C would be very, very high, and therefore it can, and since it's in parallel, therefore it can be neglected here. All right, so just for the sake of completeness, we want to point out that there is a capacitance inside the diode, as we saw earlier, and the capacitors will play a role under certain conditions. We'll just point it out in a short while. In the reverse bias, when we apply a reverse bias, we saw that the current in the diode is constant, the reverse saturation current here. And in the reverse bias also, there is a capacitance acting inside the diode here. And of course, this model is valid as long as we are below the breakdown voltage. So in that case, the current is small, and this particular model is valid here. Now, the capacitance, so normally when we reverse bias a diode, the current is very, very small. But because of the presence of the capacitor under transient conditions, a significant current can flow through the diode in the reverse bias direction also. So let me illustrate that. So let's take a simple circuit like this here, a simple voltage divider circuit. And let's focus our attention on the current flowing through this particular circuit as we apply a pulse as an input here. So from 5 to 0, 0 to 5, like this here. And since this is a pure resistive circuit, so when we have 5 here, the current would be 5 divided by 2K, 2.5 milliamperes. And the moment we switch to 0, the current abruptly switches to 0 because the resistors respond instantaneously to the voltages and currents. And so the current instantly, if we drop the voltage to 0, the current also drops to 0 here. And then when we switch it back to 5, the current again goes to 2.5, right? So this is the behavior of a pure resistive circuit. But let's add a capacitance to it. So when we add a capacitance here in parallel to this one here, so now note that the moment when we switch it on to 5 volt here, the moment we switch it on to 5 volt here, initially the capacitor acts as a short, and therefore we have a high current, 5 divided by 1K, 5 milliamperes. Eventually, in steady state, if we have enough time available, the capacitor would fully charge and will act like an open circuit, and the current would become from 5 to 2.5 milliamperes here. So that's the behavior we'll see here. Now, immediately when we switch to 0, because of the charge present in the capacitor, the current doesn't drop to 0 like in this particular case here. The capacitor now starts to discharge through 1K here and discharge through 1K here, and the current reverses. And the current reverses, and until the capacitor is fully discharged, a current keeps on flowing here. So what we are trying to illustrate through this is that Even though I've not applied a negative voltage here, it's only 5 to 0 and 0 to 5, the capacitor would cause a negative current to flow when we switch here. And this is important for us because when we come to a diode, so let's, instead of a capacitor and this thing, let's put a diode here. So in a diode also, note that there is a capacitor across the diode here, internal capacitors across the diode here. And because of that, a similar process would occur here. Diode is some kind of a nonlinear resistor in parallel with a capacitor. So similar kind of a thing would occur here. So the point is that normally when we think of a diode, we think that in the reverse bias case, the current would be in picoamperes or depending on this reverse saturation current, in nanoamperes or a picoamperes. But under transient conditions, when you have this, then there's a possibility of significant current flowing in the diode in the reverse bias direction. Note that the current is negative. And but if you wait long enough, the current would die down to 0. So in steady state, the reverse bias current would be very small. But under transient conditions, the current through the diode can be significant. So that's something that we should watch out for. That for short periods of time, the diode can be significant conduction in the diode could be taking place in the reverse bias direction also, all because of the capacitors that are there within the diode here. So we'll not bother about capacitors anymore. Let's focus our attention mostly on DC or low frequency cases here. And before we leave this particular topic, so the diodes are often characterized by what we call as a reverse recovery time. So when you switch the voltage across a diode, you go from forward bias to reverse bias. In a circuit like this, the diode conducts in the reverse bias direction for a period of time, which we call as reverse recovery time. The time it takes for the diode to recover back to its blocking state or a high low current or a high low current state here. So it takes certain time to go there, and the diodes are characterized by a reverse recovery time, and the manufacturers of the diode will provide you with data regarding that. So the waveform, reverse waveform is a little bit complicated. There may be a constant region, constant current, and then it may be falling and all that. So let's not worry about it. The important point is that the diodes take a finite amount of, a non-zero amount of time to recover back to its low current state here. And that particular time we call it as a reverse recovery time. Okay, so coming back to the analysis of diode circuit. So let's take a very simple circuit with a voltage source and a resistor and a diode. And let's say our interest is in the voltage across this particular element here, output voltage here. Now, because diode is a nonlinear element, the analysis becomes a bit complicated. So let's write down KVL. So V naught is equal to IE times R plus V naught here. V naught is the voltage across the diode. And the other equation is, we have the model of the diodes. So we said that analysis of circuits requires applications of KVL and KCL, and you require models of the elements that are there. So we've already employed the model of resistor as an Ohm's law here, and the model of the diode is this particular equation here. Okay, I equal to IS exponent V naught by NVT minus 1 here. So what we can do is we can take V naught out and express it in this particular form and substitute it back in equation number 1, and we get this particular equation here. So if we solve this particular equation, we'll get a value of I. And once we get a value of I, we'll also get a value of V naught. But the trouble for us is that the equation is nonlinear. So unlike the previous circuits that we analyzed, all the elements were linear and we obtained linear equations and they were relatively easy to solve. But the moment we go to diodes and transistors, in general, the equations become nonlinear. Both diodes and transistors are nonlinear elements, and the equations become nonlinear. And solving them requires a bit of time. So let's look at one particular approach here. In one particular approach, which we call as iterative method for solving the nonlinear equation. So what we do is we start off with a guess. So we have to solve these two equations together. Vs is IR plus V naught, I equal to Is here. So we assume, let's say the diode voltage V naught is 0.6, let's say. Then we use this particular equation, we calculate Vs minus V naught by R, we calculate the current. And once we have the current, then we go back to this particular equation number 2 and use that to calculate a new value of the diode voltage here. And so then what we do is we iterate. This is the first iteration. Then we go back and substitute the new value of V0 and calculate the current. And then we find out the new value of V0. And we do that a couple of times till we obtain convergence. Convergence meaning percentage change in current delta I by I is less than some acceptable value here. All right, so it starts off with a guess, and then you use both these equations and you iterate and find out increasingly more accurate values of V0 and also the current here. And so let's look at that. Let's take a case where we have 2 volt here, 1K here, and a diode here. And let's say the diode is described by this equation. I equal to Is exponent V by Vt. N ideality factor has been taken as 1. So it's like an ideal diode. And the rest of the parameters are given. We are analyzing this circuit at room temperature. So according to a method, assume V0. So let's, it doesn't matter unless you take a value which is very, very far out. This method works fairly well and will give you the final answer. So you may start with 0.6, you may start with 0.5, some reasonable value of diode voltage here. We know the diode voltage will lie anywhere between, let's say, 0 to 1 volt for a PN junction diode like this here, silicon PN junction diode. So let's assume V0 is 0.5. We don't know what the value of voltages are. V0 is 0.5. We get a current, 1.5 milliamperes. And we use this equation obtained from here, and we get a new value, which is 0.711. Okay, a new value, which is a better value here. So now we start the second iteration. We take this 0.711 as the guess here. We calculate the current, and we calculate the new value here, which is 0.707. We take that as the next guess, 0.707. So note that we are now working with third decimal place here, I equal to 0.293 here, and remains the same to the third decimal place. Okay, there may be some slight change in the fourth or the fifth decimal place. So we can, at this particular stage, we can say, well, we have convergence. The diode voltage has not changed to the third decimal place, and so that's the answer that we have. That the voltage is 0.707 diode voltage here, and the current is 1.293 milliamperes here. Okay, suppose we had not started with the 0.5. Somebody has started with 1 volt here. Well, let's see how it will work. So 1 volt, so current is 1 milliamperes. We find a new value which turns out to be 0.7. We take that as the new guess, 0.7. We find the new value, 1.3. We get 0.707. We take that as the next guess here. We calculate 1.293. And we obtain 0.707. So the same answer we obtain when we start off with a guess of 1 volt here. All right. So again, we converge to the same value here. So when we have circuits containing diodes, we could use iterative methods like this to find out what the voltage across the diode is and what the current through the circuit is. But as you can see here, this is as circuits become complex and contain not just one diode but multiple diodes, this method will become, using this particular method manually will become tedious and will become difficult. Of course, one can write a computer program which can do this in a better manner here, but then that will take us to, when you write a computer program to solve a circuit, effectively what you're doing is you're simulating a circuit. Right, you're carrying out a computer simulation of the circuit. So that's an approach that we'll see later on. Here we are talking about hand analysis of diode circuits. The other method is a graphical method. So the idea is, okay, so we have this particular circuit, we know this particular equation, and we know this particular equation, the diode equation. So the first equation, we can write it also in terms of I equal to Vs minus V0 by R. So effectively what we are saying is we have to solve these two equations simultaneously. And simultaneously solving two equations, you could do that graphically by plotting both these equations on a I versus V0 plot and see where they intersect. So take a I versus V0. I and V naught are the unknown things here. So I and V naught. So plot this first equation, which is a straight line. The value here would be Vs. The value here would be Vs by R. And then plot the diode equation. Plot the diode equation here. And wherever the two intersect, that's the solution. Right? So you take a circuit. We said analyzing a circuit is nothing but transforming a circuit into a set of equations, which are here. And solving those equations when they're nonlinear, you could do that by plotting them together on the same pair of axes, and wherever those you find intersection points, that would be the solution, right? So this point here is common to this equation, and this point is common to the diode equation here. So that's the solution of these two equations together. Let me illustrate that. So we took a 1N4001 diode here. So this particular diode is there. This is the equation of the diode. And we are solving it for a case of where source voltage is 2 volt, supply voltage is 2 volt, resistor is 10 ohms. So that's the line here. And the intersection is at this particular point. And we get an answer which is 0.77 and I is 0.12 amperes here. So you could use a graphical method. This is also called a method of load line method here, because normally this resistor may be a load resistor here, and you're plotting an equation. This is nothing but a linear relationship for this particular resistor, or an equation for if it's a load, it's a load line here. It's a line describing the equation of the load resistor here, and that's why this method is sometimes called the method of load line method here. All right, so but both of these methods that we just saw, iterative methods and the method of load line, these are complicated techniques, will take a lot of time to solve. And also we said that if you have more than one diodes, things become really messy. So for hand analysis, for quick analysis of circuits, we need simpler models. And simpler models basically mean that we need linear models, because linear circuits are easy to solve here. So that takes us to the issue of, let's spend some time and think about what do we mean by these models here, okay? So what is a model? And so an important point to remember is a model, in our context, a model is a representation for a purpose. So when we're talking about a model for a diode, we are talking about a representation of a diode in a mathematical or a circuit representation of a diode for a particular purpose. And as you change the purpose, the models change. Okay, so let's look at this particular point here. So if you pick a resistor in the lab. Well, if you pick a resistor in the lab, a physical resistor, a real practical resistor in the lab, there are, I'm trying to illustrate that there can be many models, but two models of a resistor like this. One is a simple model with a resistance R, but this practical resistor that you see here, practical element that you see here, it would also have certain inductance. There would be a lead here, and you know that anytime a current passes, there's a magnetic field associated with the current, and as the current changes, there's an inductance also. So there's an inductance also, okay? And between these two leads, there would be a capacitance also. The air acts as a dielectric, and the two leads are at two different potentials here. And so through the air, there's a capacitance also here. So if I think of a practical resistor is not simply an R. A practical resistor is an R and an L and a C. So that's this one we would call as a simpler model. This one is a more complex but more accurate model. Right, so for the case of a practical resistor, we can see that there are these two models that are possible here. A simple model, but obviously less accurate, and a complex model, but more accurate. And in general, you would find that no matter which element you take, you can build a variety of models for that particular element. And a variety of models with different accuracies and different complexities. So in general, as you may expect, that the accuracy of a model will increase with complexity. Not in this linear manner, this is just a schematic illustration, but what it is saying is a complex model would in general be more accurate. a simple model would in general be less accurate. So at this point, you may also wonder that if I have an accurate model, why do I need an inaccurate model? And but you also realize that an inaccurate model is also simple. So there is a value attached to the simplicity of the model here. So what is the use of a less accurate model? All right, so less accurate model, let's look at it. So suppose I want to build a circuit like this here, right, with two resistors. And with two resistors like this, and I analyze this particular circuit using these two different models. In one case, I think of these two resistors as simply R, and in the other case, I think of them as C, L, and R, as a more complex model, more accurate model here. So if I analyze it, so in first case, this circuit boils down to simply R1, R2. In the next case, it boils down to R1, L1, C1, R2, L2, C2. So let's analyze this circuit. Now, obviously, a simpler model will make analysis simpler. So in this, when we use a simple R here, V2 by Vs is simply R2 by R1 plus R2. When I use this more complicated model for a practical resistor L, R, and C, well, V2 by Vs comes out like this here. So at this point, you have to ask yourself, why are you doing the analysis? What is the purpose of your analysis? If the purpose of your analysis is to understand what the circuit does, well, this circuit, this expression, the use of a simpler model is telling me that my circuit is a voltage divider. While if I look at this particular one is not able to make out what the circuit is doing. Even the effect of R2 and R1 and all that is all jumbled up and implicit in this particular equation. One is not able to understand. If somebody gives you V2 by Vs as this expression and doesn't tell you what the circuit is and asks you what is the circuit doing, well, it will be hard for you to figure out what exactly is the circuit doing. So when we use a simpler model, what it does is it makes the analysis simpler. You're able to quickly calculate, get an estimate of the numbers that are there in the circuit, and also you're able to obtain a result which is understandable. You can understand what the circuit is doing, and that's an important part of whenever you're looking at something new for the first time. It's important to understand what that unknown circuit or unknown system is actually doing. So a simpler model will help you obtain a result. The result final value may not be as accurate, but the understanding that you will obtain would be valuable. So the results of analysis are easier to understand when you use a simpler model. So that's one very, very important aspect of why we look for simpler models, even though we know that they may not be very accurate, but using them, we can obtain results like this and we can understand what the circuit is doing. The other thing is, you're analyzing the circuit to understand, but eventually you would like to design the circuit. So let's say you are asked to design a circuit such that V2 by Vs is 0.2 at 1 kilohertz frequency. Okay, and you have these two. In one case you use a simple model, in one case you use a complex model. But this is you're going to apply, let's say, a sinusoidal signal, and what you're looking for is that the output voltage versus Vs is 0.2. So when we use a simple model, R2 by R1 plus R2 equal to 0.2, we can very easily get R1 by R2 4, and thereby we can choose a value of R2 equal to, let's say, 1K, R1 is 4K, and the design is over. Now think about doing this using this circuit. V2 by Vs is given here. So now how do you figure out what is the right value of R2 and R1? Note that in design, in analysis, you get an equation like this, and you have all the values of R2, L2, and C2 and all of that, and you just plug it in and you get the value V2 by Vs. Design is the inverse problem. You're given the left-hand side and you have to figure out what the appropriate right-hand side values may be. Now note that there may be different kinds of resistors available with different values of L2 and different values of C2. So your job is to figure out what kind of a resistor should I use for R2 and what kind of a resistor should I use for R1 to arrive at 0.2. So you can see that a complicated expression like this, even though it's accurate, you will not be able to, or you'll find it very difficult to use it to analyze or to design the circuit, to figure out what the right values are. So that's the other trouble with accurate models. Accurate models are complex, Analysis is difficult with them. The results that you obtain are difficult to understand. And when you try to use those accurate models, the accurate expressions for design, you get stuck. You're not able to do an inverse of this particular equation to figure out what the right values are. So what you're seeing is, what we're trying to say is simple models are useful. But we also realize that complex models are also useful. They are more accurate. So what is the role of a simple model and what is the role of a complex model in a design? So this is not just about circuit design. This is true of other engineering designs also. So the idea is that when you're doing a design, and design is an inverse problem, you want something and you have to figure out how to obtain by combining elements. So when you're doing design, simple models help. So you use simple models, they will result in simple expressions, and you use that to carry out the design. But we also realize that when we use these simple models, simple expressions to carry out design, our design is not going to be accurate because the simple models are inaccurate. So what we do is, after we do the design, we simulate a design. We use computer simulation to evaluate a design, to see how much inaccuracy or how much error is in the design. So we use simulation. Now simulation is nothing but analysis which is done by a computer. So when we are trying to evaluate a design, we are using a computer to simulate a circuit, and then we use the accurate models here. As accurate a model as we have, accurate but complex model here. So we use those models to simulate a circuit. And once we simulate the circuit, we may find that the result is not what we want. And therefore, we may go back and tinker with the design here. We may modify some component, increase the value of R1 or reduce the value of R2, and then simulate it again. And then check whether we are happy with the result that we get. If we are not happy, again, we try to fine-tune the design. So note that a coarse design is obtained by using simple models, and a finer design is obtained through this kind of an iteration here, through some design modification, then simulation, and then design modification. Once you're happy with this, then of course you can take your design and then you can finally implement it. You implement it as an IC or on a breadboard or a PCB and all that, and you can try. But note that even when you implement it, you're going to use a real physical component, and a real physical component is always a little different from even the most complex model here. So there's always a chance that after you implement and you do experimental measurement, things are not as you expected here, and then you may have to go back and tinker with the design again. Okay, if your models are very accurate and realistic, then after you implement it, you'll find the circuit works according to your expectations. But sometimes when you're trying to design and implement something which is very novel, you may find that you didn't capture everything in a model, and therefore even after implementation, after simulation and all that, there may be some surprises, and you may have to go back to the design stage here. So this particular slide tells you the role of simple models and the role of complex models. So accurate and complex models are for computer simulation, and simpler models are for us to analyze the circuit, understand the circuit, and to obtain the initial design. So if we want a simpler diode, we don't want to use a nonlinear diode model, because we just saw a nonlinear diode model requires an iterative method or a graphical method, and it's not easy to use here. So what we are looking for is basically for the diode a simpler and a linear device model. So one of the models that one uses for a diode is very simple model is in the forward bias direction. We model the diode as a battery here with some voltage here, V gamma. And in the reverse bias case, we know that the current flowing in the reverse bias case is very small, and we model it as an open circuit. Note that this is a simplified version. The actual diode behaves, we've already seen, is a nonlinear expression of current versus voltage here. And even in the reverse case, there is a current flowing, but this is a simpler model that in reverse bias case, we can think of it like an open circuit, and in the forward bias with a battery like this here. Now, what should we take as this voltage here? So if we are going to model this particular diode, what voltage should we take? And many times you will find in books and various places, and even in this particular course, a common value for a silicon PN junction diode that we take is 0.7 volt here. And so let's look at this here. Okay, so this 0.7 here, note that is just a value, and it may be accurate, it may be reasonable in some cases, it may be unreasonable in some other cases here. Okay, so let's look at it here. So let's see this particular diode that we have with saturation current and all that given here, and this is the circuit with 1.7 volt battery here. And to see how accurate, suppose I substitute a diode by a 0.7 volt model here, and so I will get a certain value of current in the circuit here. And the issue is, how accurate is that current? Well, note that R in my circuit could be 10 ohms, could be 100 ohms, could be 1 kilo ohm, could be even 1 mega ohm. I mean, these are the typical resistors that we commonly use in circuits. It could be 10, 100, 1K, all kinds of resistor values that are there here. And how well does my 0.7 volt model, if I replace the diode by a 0.7 volt model, how accurately will it give me the value of the current? Okay, so simpler 0.7 volt model, if I substitute in the forward bias, we know that the diode is forward bias, which simply give me current is I equal to 1 by R. Okay, so let's compare the current given by this model versus current given by the accurate model here. Okay, so we are looking at this particular circuit, and so what we did was by using an accurate model, and for various values of resistor here, resistor of 10 ohms, 100 ohms, 1 kilo ohm, 10 kilo ohm, and 1 mega ohm, right? And by using the accurate model, I determine the diode voltage here, and the diode voltage goes like this here, this solid line here. Because note that as you use higher and higher values of R, the current reduces and the diode drop also increases, also reduces here. So for 10 ohms, the diode drop is around maybe 0.81 or 0.82 or so, and the diode drop keeps on reducing here. While what we are doing is, in a simpler model, we are replacing it by 0.7 volt here. So that 0.7 volt approximation would be accurate at this particular point, maybe at 1 kilo ohm resistor. And if I have less than 1 kilo ohm resistor, 0.7 volt is underestimating the diode drop. And if I have higher values of resistor, 0.7 volt is overestimating the diode drop here. Okay. But note that the amount by which is underestimating and the amount by which it is overestimating is not very large. Okay. And so in many situations, then the 0.7 volt will not result in significant error. And but keep in mind that the diode drop will change with the current and can be anywhere. Let's say if you have a 10 ohm resistor, can be anywhere from 0.82 to almost like maybe 0.52 or so. So it is varying almost by 300 millivolts here. And what is the error in the current? So the error in current, if I use a constant diode model, 0.7 volt, note that the error here is about maybe minus 12% here. The error is about 12% here. Okay. And if, many times when we are doing hand analysis of circuits, anything which is, if the error is less than 10% or so, we are okay with it. We realize that we are using a simpler model, so errors are going to be there. And if the errors are, if my result is accurate to within 90% of the final value, then, as an initial value, that result is reasonable. Okay, so let's take a different diode. The previous one was 1N4007, so this one is 1N4148. So let's look at the same thing if I do here for the same different values of resistor here. And the errors are, note that in this case, the error becomes, for a different diode, the error becomes as large as 30% at 1 mega ohm here. So whether my 0.7 volt model is accurate or not depends on the nature of the diode, depends on the kind of currents that we have in the circuit. and the error, in many cases the errors are within maybe 10%, but there are times if we are not careful, for example, if we use a diode like this here, if we use a diode 1N4148 with this kind of a model, note that the ideality factor is 1.91. If we use that particular model and we substitute this as 0.7 and we have a 1 mega ohm resistor here, well, the result is going to be fairly off from what we will get here. The result would be about 30% error here. So one has to be careful when one is using 0.7 volt model. In some cases it may give reasonable results, in some other cases may not be that reasonable. Okay. The other point is that constant diode voltage approximation becomes worse as the applied voltage approaches the diode drop. So, we are assuming that the voltage drop across the diode is 0.7. Well, we know it's not 0.7. It could be 0.6, it could be 0.5, it could be even 0.8. But that error here will not matter much if this voltage is, let's say, 100 volts. Because we are talking about errors in 0.1 or 0.2 volt here. But if this voltage is 1 volt here or around that value, then the error will become significant. Okay, so let's look at this particular point here. So the current I flowing will be equal to Vs minus Vd. Vd is the diode drop by R. And the error in current results from the error in the voltage here. So we are approximating it by 0.7. We know it is not 0.7. So there's an error here. So the error delta I will be equal to minus delta the error in diode voltage by R. And the percentage error delta I by I will be equal to minus delta Vd by Vs minus Vd. So it shows that the percentage error, this is what we are interested in, not the absolute value here, but the percentage error that is there here. We see that the percentage error in current starts to become significant when Vs starts to get closer to Vd. So that tells us that when we are deploying our simple model, we should be careful that the voltage in series with it is significantly larger than the diode voltage here. If it starts to become very close to Vd, then we'll start incurring a lot of error that is there here. Okay, so that's something that we need to. So for example, if I take this particular circuit and I look at it with 1.7 volt battery here, then the error in the current is 9%. But if I apply a 0.8 volt battery here, 0.8 volt battery here, then the error is 63%. So when you have low voltages in the circuit and the voltages are comparable to diode voltages, you should be careful in terms of substituting a constant diode model. In that case, you may want to go back and use a more accurate model that is there here. Or a different approximation. Instead of taking 0.7, maybe a different approximation you should try for the diode voltage here. So sometimes a slightly better model for diode is used where the diode in forward bias is approximated not just by a battery, but by a resistor also. So this takes into account that the voltage drop across the diode changes with the current. Okay, so in the earlier case, the voltage drop across the diode was constant, and we know that it varies. So this particular model takes care of that point here by adding a resistor here. And the model is valid for V greater than V gamma. And for reverse bias, we still use an open circuit here. So basically what we are doing, if you look at this particular case here, we are basically taking a diode and approximating it by a piecewise linear approximation. So this is a I versus V of a normal diode. And we are approximating the diode by, we are saying the current is 0 here, and then it's linearly changing here. This is the value which is V gamma, and the slope of this particular one is equal to 1 over RF here. So this is what we are trying to do. In exponential graph, we are trying to approximate it by this piecewise linear segments, one segment here and the other linear segment over here. Okay, so this is what we are trying to do here. And note that you can do that for different ranges of current. Suppose you're working in a range of current which is around 100 milliamperes. So you could do that and you may get a value of V gamma and you get a value of RF. If your circuits have currents in the range of microamperes, you do a I versus V where the current is in microamperes. And then again, you can do this kind of a piecewise linear approximation and you'll get different values of V gamma and different values of RF. Okay, so let's illustrate that. So in this case, note that we've taken a diode characteristics which is in the range of 50 milliamperes, 0 to 50 milliamperes here. So why have we taken that? Well, suppose you analyze your circuit which contains a diode and you know that your currents are somewhere in the range of tens of milliamperes. It could be 20, 30, 40, somewhere around that. So then this kind of a scale is meaningful. In this case, we will approximate it like this here. We'll approximate it like this, and we get V gamma equal to 0.75 and RF equal to 1.4. So in 0 to 50 milliamperes, we take somewhere in the middle a current range 0.25, draw a tangent here at 0.25 and let it intersect with a constant here, okay, at this particular point here. So our diode model then becomes a cut-in voltage of 0.75 volt, V gamma, and a resistor of 1.4 ohms. Now the same diode, if I now look at a different current range here, 0.0005 here, right? So a different current range. Now, so 0.25 milliamperes is in the middle here. Now I again do a piecewise linear approximation and draw a tangent at 0.25. And now we approximate it as 0.63 and RF is 150 ohms. So note that the same diode is being approximated by two different models. If you're working in this current in less than current in the range of, let's say, 0 to 0.5 milliamperes, then this kind of a model is appropriate, 0.63 volt and RF of 150. In the previous case, if you were working in the current range of 50 milliamperes, then a different value of V gamma and a different value of RF was necessary here. Well, this one was a little bit more accurate model, but we can build even a simpler model. So this is the model that we talked about, V gamma. Well, we can build even a simpler model. We can say in the forward bias, the diode is like a short circuit. And in the reverse bias, the diode is like an open circuit, right? So this is what we call as an ideal diode model here. Forward bias, short circuit, reverse bias, open circuit. That's the simplest model that you can build of a diode. This one is a little bit more complex, better, where in the forward bias you approximate it by V gamma and in the reverse bias with the open circuit here. So already we can build 4 different models. We have this model, which is represented by this equation. Then we have this model here, where we approximate the diode in forward bias with a battery and a resistor, in reverse bias with an open circuit. Then we have this diode, this model here, where we have, we ignore the resistor here, we just take the diode drop as constant, independent of current. And then we have even simpler model here, right? So we have 4 different models already. And the simplicity is increasing in this direction and accuracy obviously increasing in this direction here, right? And each one of these models is useful. As we said, remember that a model is a representation for a purpose. And somewhere you may find that this model is adequate, somewhere you may find this model is adequate, somewhere you may have to use this. And there may be situations where none of these 3 will give you a reasonable result. You have to go back to this nonlinear diode model here. Okay. So in general, use the simplest model that will yield results with the desired accuracy. So if we take a result like a circuit like this, and if I deploy this simplest model, ideal diode model, well, I will get a result which is very quick, 10 by 10. I don't even have to do the calculation. We know that the diode is forward biased, 10 by 1 gives me 10 milliamperes. So that's the advantage of the simplest diode model. In the next case, I replace it by 0.7 volt here. And so that gives me 9.3 milliamperes here. In the next case, we approximate it by 0.7 and a 10 ohm resistor here. This one gives me 9.208. And finally, I use the nonlinear diode model, and that gives me 9.24 milliamperes here. So note that this one was the easiest to use, and this one is the most complex to use, and so is the most accurate answer here. So the error is 8.2%, the error is 0.65%, and the error is 0.34% here. So in this case, if we are happy with, in an analysis with errors less than 10%, then even this model is fine with us. Even this one is okay. And this one is certainly very nice here. It gives us error less than 1%. There's no point in doing this, going to that small an error. Keeping in mind that keeping in mind that, whenever we are taking a practical circuit and modeling it as a schematic like this, there are many approximations being made in that. Remember that even the resistor 1K may not be exactly 1K. It may be 0.9K because of tolerances. Similarly, the diode IS and saturation current may not be what we think it is, because there's a tolerance associated with everything. So sometimes there's no point in carrying a very accurate analysis because the values of the components itself are not that accurate. You don't know whether it's really 1K. You don't know whether it's really 10 volt. It could be a little bit higher or a little bit lower. And therefore, this is something like an artificial accuracy that is there here. All right, so this may be fairly reasonable. Even this is fairly nice here. On the other hand, let's say we are working with 1 volt. And so if I use the simplest model, I get 1 milliampere. If I use the next model here, I get 0.3 milliamperes here. Note the wide difference in the results that we get. If I use this slightly more accurate model, I get 0.297. And if I use this, I get 0.329. So the error is 200%. It's obviously this particular one we cannot use. And which is obvious because we said that when the voltages in the circuits are close to the diode drop, you should be careful and not use very, very simple models here, right? So 200% error here, 8.8% error here, 9.7% here, and the final value here. And so the reason why we didn't get a very good answer here is because there's a problem with the model here. We can build a better model and get a better result for this particular case. So even in this case, this kind of a model gives us with error less than 10%. So we are okay, this constant diode model here. Okay, so as an example, suppose let's take this different example. We are given a slightly more complicated circuit. And we want to find out what is the current flowing through the diode here. So in circuits like this, many times we don't know whether the diode is forward biased or reverse biased. That's the first problem in a circuit like this here. So, sometimes it's easy to tell, but sometimes it's not that easy. Okay. So what we can do is we can assume, for example, that the diode is forward biased. We can assume that the diode is forward biased and then carry out the analysis. And once we do the analysis, we'll get the current flowing. And if the current is in the right direction, then we know that our assumption was correct. But if the current comes out to be in the opposite direction, going, let's say, from here to here, then our assumption is incorrect because current cannot flow through the reverse bias diode. That much current cannot flow through the reverse bias diode. So assumption is incorrect. And then we can take the diode as reverse bias and redo the analysis. Okay, so let's do that. Let's assume forward bias. And when we assume forward bias, we are using a ideal diode model here. Okay, so we short it. Ideal diode model. We analyze this particular circuit. And we analyze this particular circuit and we get the current. So we get a current of 4 milliamperes. And current is positive, so our assumption is correct. So that's the final answer. But let's look at this one here with slight change here. Okay, so again we assume forward bias. Again we try and calculate the current, and the current comes out to be, note that the diode current comes out to be 4.5 milliamperes. Now 4.5 milliamperes, the current is going like this here, 4.5. And so when we come back, 4.5 milliamperes, that much current cannot flow in the reverse bias direction here. So which means our assumption of forward bias is incorrect, right? So it is incorrect. And so we have to go back and solve the circuit by assuming it to be open circuit here. So now you open it and you calculate, you do the analysis and you'll get the right answer, because now we've already proved that the diode is not in forward bias, so it has to be reverse bias. And in reverse bias is open circuit. So solve the circuit and get the answer that you're looking for. So before we end, we had this diagram here. We said that simple models are useful for understanding the circuit, for initial design, and complex models are used with computer simulation to evaluate the design and fine-tune the design. So let's look at a very simple example before we close this particular lecture. So suppose we have to design this particular circuit. We have to design a circuit which is given here, and we have to find out the values of R1 and R2. And let's say the diode is given. And we have to find out the value of R1 and R2 such that the output voltage is 2.5 volt. So what we can do is we can use a ideal diode model. Ideal diode meaning assume it to be short. So we get R1 and R2. And then the design becomes very simple. We get R1 and R2 equal to 1K will give us 2.5 volt, right? And so that's the advantage of simple models. We are able to analyze quickly, and we are able to obtain the design quickly here. So we are able to obtain the design, but we know that the design is not going to be correct because the diode is not a short. There's a drop here which we ignored, and therefore our design is not correct. So what do we do? So after obtaining the design, we simulate it. So let's do the simulation. So we go back and do the simulation here. So this is our circuit here. 5 volt here, 1K here, and 1K here. And we simulate it and we try and find out what is the output voltage here. So the output voltage turns out to be 2.747. So we wanted 2.5, but it is 2.747. So that's where now, whenever we design a circuit with simpler models, it's going to be a little bit inaccurate. Note that it's not too inaccurate. We wanted 2.5, it is 2.7. So now is the time to fine tune the design. Now the advantage of using simpler models is it helps us understand the circuit. So when we see 2.7 and I want to reduce it, bring it to 2.5. So one of the ways that you can, because you understand the circuit now, one of the ways that you can think of if you want to reduce it from 2.7 to 2.5, you can increase the value of R1. So let's increase the value of R1 to, let's say, let's fine tune it 1.1. Well, 2.638. Let's do 1.2, 2.539. Well, let's do 1.3. Well, it became less, so we know it lies somewhere between, let's say, 1.25. All right, 2.492. Let's reduce it to 4 here. Okay, so we may be happy with 2.502. So a little bit of fine tuning is required to come back to now the final value that is there here. Okay, so the final value then for our design. So after fine tuning, we can use this as 1.24K, and this is 1K, and then this gives us 2.502 here. All right, so let's stop here.